Okay, good morning, everyone. Here I am lecturing to an empty classroom. We are going to begin where we stopped off last time in the Chapter 1 class notes. You should now have downloaded those notes and have them in front of you for reference. Last time we started by looking at the generic two-port circuit element as shown here, a black box which we call our two-port with a pair of terminals which we denote as port 1 and another pair of terminals denoted port 2, voltages and currents at the two ports defined using the passive sign convention so that in both cases at port 1 and at port 2, note that the current flows into the terminal that's marked as the plus terminal, both on port 1 and on port 2. So make sure you make note of that convention. You can generalize this two-port circuit to an n-port circuit where n is any number by adding pairs of terminals with voltage VI defined at each terminal pair and appropriate currents I sub I, which would flow into the positive terminal of the ith port. Well, in any case, our interest is going to be simply with these two-port circuits. We won't need the more generalized concept of an n-port. Last time we looked at the four parameter sets that are commonly used at low frequencies, the Z parameters, Y parameters, H parameters, and ABCD parameters. By the way, these ABCD parameters sometimes go by the name of chain parameters. In any event, as long as the two-port network is a linear network, no matter how complex, the relationship between the circuit variables, voltage and current at port 1, and the circuit variables, voltage and current at port 2, the relationship between these four variables is going to be a linear relationship that can be written as a set of two equations in two unknowns. You choose whichever of these four variables, voltages and currents at the two ports, whichever pair of those four variables you would like as your unknowns, and the other two you assume are known quantities, and write equations for the unknown quantities in terms of the known quantities as linear combinations. And that's how we end up with the definitions of the different parameter sets. For the Z parameters, we treat the voltages as being the unknown quantities. V1 and V2 are the quantities that we would like to compute based on known values for the port currents, I1 and I2. So in general, we write V1 as a linear combination of I1 and I2 with coefficients Z11 and Z12 multiplying the currents. V2 as a linear combination of the two currents I1 and I2. And that's how we define the Z parameters. There's the matrix form of that same set of equations that I've written up above, where you can now define a Z parameter matrix. You can do the same thing solving for currents as your unknowns in terms of voltages as the known quantities to end up with the Y parameters as shown here. The hybrid parameters used in electronics are obtained by treating V1 and I2 as the unknowns in terms of the known quantities I1 and V2 and writing two equations for the two unknowns in terms of the two known quantities, which can be written in matrix form as shown here in terms of the matrix of H parameters of the network. And then finally, the ABCD parameters, the chain parameters, they're defined as follows, where we treat as unknowns that we would like to solve for V1 and I1, the voltage and current at port 1 on one side of the two-port network, given the voltage and current at port 2 as the known quantities, V1 and I2, or more precisely, minus I2, where I'll explain where the minus sign comes in just a moment. And the coefficients of the two equations and two unknowns for the linear relationships here are the ABCD parameters written as the chain parameter matrix shown here. Okay, now, these parameters are both defined and can be found in terms of very simple formulas. There are simple formulas for all of the H parameters and Z parameters and Y parameters and ABCD parameters, and corresponding simple measurements that you can make in the laboratory to measure all of these quantities for any given two-port network. They are all for these four low-frequency parameter sets. They're all definitions and measurements that are in terms of open circuit or short circuit conditions on one of the two ports of the two-port network. What I'm saying is, in order to define these low-frequency parameter sets, and in order to be able to measure the low-frequency parameters, what you have to do to your two-port is either with pencil and paper in a calculation, place a short circuit or an open circuit on port 1 or port 2 and do calculations on the circuit or do measurements on the circuit. Or actually in the laboratory, place an open circuit or a short circuit at one of the two ports. Let me explain this process on paper for you with an example of a particular circuit. So let's turn to the overhead for a moment. Wow, that camera is a little bit crooked. There we go, that's a little better. And let's take a look at a particular example. Let's say that we were given a pi type arrangement of three impedances, Z1, Z2, and Z3. These are our general impedances. They could be resistors or inductors or capacitors or combinations of such elements with their impedances given by the usual expressions R j omega L, 1 over j omega C, and so on. So here's my pi network. And to treat this as a two-port, we define voltages and currents at the two ports. I'll call the port on the left-hand side port 1 and port on the right-hand side port 2, so that I have voltages and currents at the two ports defined in the usual way for the passive sign convention applied to this particular two-port circuit. All right, let's do two calculations. Let's find two things here for this circuit. Let's, for example, find the value of Z11 for the Z parameters. Let's find D of the ABCD parameters. Let's make those our two examples. Here's how I would go about finding Z11. Let's see here. The basic equation that we use in our very definition of the Z parameters tells us this. This is one of our two linear equations that we used to define the Z parameters. How can we solve that equation for Z11? Without having to know the value of Z12 first? Well, I could solve that equation for Z11. This is what I want to get, Z11. If only this second term wasn't there. If that second term wasn't there, then Z11 would just be V1 divided by I1. What could we do in our original circuit that would get rid of that second term in the equation defining the Z parameters here? How about if somehow or another we could enforce the fact that I2 be equal to 0? That is to say, in a measurement or in a calculation, let's force I2 to be equal to 0. Now, I2 is the current flowing into the upper terminal up here. So if I2 were equal to 0, that means that term would be equal to 0, and Z11 would just be equal to nothing more than V1 divided by I1 when I2 is equal to 0. what that means in terms of the circuit is don't place any element here over on port 2 of this network. Make a measurement of V1 and I1 over here on port 1 when there's no load present on port 2. Leave port 2 open circuited. If port 2 is open circuited, then there's going to be no current flowing into or out of port 1. Right? I mean, by Kirchhoff's current law, the sum of the currents flowing into or out of any particular node must be equal to 0. Well, there's only one path for current to flow in or out of this node. That's that wire right there. And Kirchhoff's current law says the current flowing into or out of that node must be 0. As long as there's no other piece of wire hooked up to that upper terminal, that means I2 is equal to 0. Open circuit, port 2. And then find the ratio of V1 to V2. So you can think of Z11 as being V1 divided by I1 when I2 is 0, or V1 divided by I1 when port 2 is open circuited, or the impedance looking into port 2 when port 1 is open circuited, or what we often define as the input impedance, or the impedance looking into port 1, the same thing, when the output of the circuit, port 2, is open circuited. Okay, here we go. Let's do some actual calculations then. Leave port 2 open circuited. That is to say, just consider the circuit that's drawn at the top of the page as is. Nothing connected to port 2. What's the input impedance? Well, let's see here. What do we see looking into this port? This is a problem I could give to students in Circuits 1. I've got these two impedances, Z2 and Z3, in series with one another. Whatever current flowed through Z3 would also have to flow through Z2 because there's no current flowing through that other branch, I2. So Z3 and Z2 are in series. They are, in turn, the series interconnection of Z2 and Z3 in parallel with Z1. That is to say, the voltage across Z1 is the same as the voltage across the series combination of Z2 and Z3. So the moral of the story is the input impedance is Z1 in parallel with the series combination of Z2 and Z3. I write that in this way. The input impedance is Z1 in parallel with the series combination of Z2 and Z3. The plus sign represents a series combination. You just add the two impedances to get the impedance of the series combination. The double vertical slash there represents parallel combination. If you've got two elements in parallel with one another, the impedance of the parallel combination of A and B would be A times B over A plus B. Okay, well, I can use that. A times B over A plus B. And there you have it. So tell me what the elements are, what their impedances are, and I can simply plug into this formula right here in order to calculate the input impedance when the output is open-circuited, which is Z11. Okay. So much for finding Z11. All right, let me turn back to the definitions of the ABCD parameters. That's the matrix equation at the top of the first column on page 2. I need the second row of that matrix equation. That's the one that's in terms of D. And reading off that equation, it says I1 is equal to C times V2 minus D times I2, where that minus sign was that curious minus sign that was associated with I2 that I'll be explaining presently. Well, in any event, we're trying to find D. We could do that. We could solve this equation if only the first term there vanished. Then D would be the negative of I1 divided by I2, right? How would we get V2 equal to 0 in the original circuit? Now this is the calculation we've got to think about, or this is the measurement we have to perform. We've got to find the ratio of currents at the two ports when V2 is equal to 0. How would we make V2 equal to 0? I can think of one very simple addition to make to this circuit that would enforce V2 being equal to 0 always. How about if you just connected a piece of wire short-circuiting port 2 as shown here? This is nothing more than a short circuit. If I put a piece of wire there between the two ports, between the two terminals at port 2, sure would make V2 equal to 0. All right, so what that tells me is that D is equal to minus I1 divided by I2 when V2 is equal to 0. Okay, now what we have to do is somehow or another figure out that ratio of I1 to I2. I can use current division to accomplish that calculation as follows. Let's see if you can see this with the circuit up above. Minus of I2 would be equal to a current division factor times I1. And the current division factor would be equal to Z1 divided by Z1 plus Z3. Okay, so here's what I claim. I claim that you tell me what I1 is, and all I've got to do is multiply I1 by an appropriate current division factor to figure out the negative of I2. Not I2 itself, but the negative of I2. Let's look at that original circuit, imagining that that short circuit is in place. Okay, now first of all, if the short circuit is in place, we no longer have to even include Z2 in the circuit at all. Z2, that impedance Z2 is short-circuited. Any current flowing on this wire or on that wire is going to flow through the short circuit. It's not going to flow through the impedance Z2. So you could effectively take the impedance Z2 right out of that circuit altogether. Ignore Z2, it has no effect. Okay, well, here's the current I1. What happens to that current I1 when it enters terminal 1? It divides I1 partially, flows down here through Z1, and the other part of I1 flows there through I3. This is the portion we want. Why? Because if I can tell you what that current is, it's equal to that current. Well, the negative of that current, right? This current is flowing to the right. This current that we defined as I2 flows to the left, but it's the same magnitude. So the current I would find by current division, which would tell me how much of the current I1 flows in this direction through Z3 with a negative sign, would give me the current I2 required. Remember, there is no current flowing through Z2 because it's short-circuited in this case. All right, then, what does current division tell us? Current division tells us that if you've got a network of two impedances in parallel and you've got a total current flowing into the parallel connected elements, the amount of the current flowing through one of the elements is the total current times the current division factor, where the current division factor is the impedance of the element that you're not trying to find the current through, divided by the sum of the two impedances. So the current division factor to use to figure out this current that flows through Z3 is Z1 divided by Z1 plus Z3. Remember, Z2 has no effect. So the current division factor is exactly what I wrote down there towards the bottom of the page, Z1 divided by Z2 plus Z3. That will give us this current, which is the negative of I2. hence the equation that I wrote. Negative of I2 is equal to I1, that's our total current, times the current division factor, which we just explained is Z1 divided by Z1 plus Z3. Well, D is minus I1 divided by I2 in this case. There's I1, there's minus I2. Put that over on the other side, and I guess there's our result, Z1 plus Z3 divided by Z1. The calculation that I've done for these two particular examples of Z11 and D are exactly the same sort of calculations that you do for any of the other of the total of 16 parameters involved in the low-frequency parameter sets. They're all going to be in terms of either calculations or measurements in terms of open circuit on one or another of the ports, or short circuit on one or another of the ports, depending on which variables you're trying to zero out, get rid of in the set of linear equations defining the parameters, so that you can solve for the other of the parameters that's in that particular equation. If it's a current you're trying to zero out, leave that particular port open-circuited. Current guaranteed will be 0 at that port. If it's a voltage that you're trying to zero out, short circuit the corresponding port in the circuit and do your calculation or do your measurement with that short circuit in place. The voltage at that port that's been short-circuited will be 0, guaranteed. All right, let's turn back to the class notes now. And take a look at what you do with the parameter sets to come up with the parameters for interconnected two ports. This is a very interesting and common type of thing to do with a pair of two ports. And I'm going to assume that we've got two ports, one called two-port A and the other called two-port B, and I'm going to connect them together in various ways. Of course, we could have n two ports, where n is any number, and have them interconnected in a whole bunch of different fashions. You can always build up that interconnection of n two ports by considering them one pair at a time, coming up with an overall single two-port that represents the interconnection of the two that you just considered, and take that new single total interconnected two-port and now connect that two-port up to another two-port and come up with yet another total interconnected equivalent two-port for now the three two-port networks, and so on and so forth to get your complete interconnection of n two ports. So dealing with two ports is fine. That will give us an interconnection of as many two ports as we desire. The first interconnection that I'm going to look at between our two-port networks is the so-called series interconnection of a pair of two ports. This is the connection between the two ports, between the pair of two ports, that is defined as a series interconnection. It's not 2-port A followed by 2-port B with wires connecting the output of the first 2-port to the input of the second 2-port like you would a pair of resistors. That's not a series interconnection. We'll look at that one. That's coming up. But that's not what we call a series interconnection. This is the definition of the series interconnection of a pair of 2 ports. And we would like to come up with expressions for the parameter set that would describe the entire black box inside of this dotted line, which consists of 2-port A and 2-port B with this particular interconnection between the two. We'll find that the parameter set to use, if you're using low-frequency parameter sets, the best parameter set to use in this case is the Z parameters. Because in that case, the Z parameters of the series interconnected pair, that is to say the overall Z parameters or the Z parameters total Z parameters here, consist of nothing more than the sum of the Z parameters of the individual 2 ports, 2-port A and 2-port B. This is a matrix equation. These are all 2x2 matrices. And what this matrix equation tells me is actually 4 equalities. It tells me Z11 total is equal to Z11 of 2-port A plus Z11 of 2-port B. And the same thing for Z12, Z21, and Z22 of the total interconnected, series interconnected 2 ports. Simply sum the corresponding Z parameters of the individual 2 ports. Here's a circuit example of a pair of interconnected 2 ports. You can consider the transistor here to be 2-port A. Consider this shunt resistor connected to the emitter of the transistor. Consider that as 2-port B. And then the overall 2-port would be the transistor with a shunt emitter resistor connected to it. This is just a piece of wire here and a piece of wire there in case you really want to see the 4 terminals connected up to the resistor and 4 terminals connected up to the transistor. Otherwise, for purposes of circuit analysis, you could just draw that as a single straight piece of wire connecting the emitter to the resistor. Okay, so that's a very common type of circuit, and if you knew the Z parameters of the transistor and the Z parameters of the resistor, just add them together to come up with the Z parameters of the overall transistor with a shunt emitter resistor. Okay, here's another possible interconnection between a pair of 2 ports. This is the so-called shunt interconnection. This is how it's defined. 2-port A and 2-port B connected together. In this way, the top connection of port 1 for 2-port A is also the top connection for 2-port B. Top connections on port 2 are also the same. The bottom connections for 2 ports 1, A and B, are also the same in this circuit. And we would like to have a parameter set that would give us parameters for the overall circuit inside the dotted box, the shunt interconnected pair of 2 ports. In this case, your best bet would be to use the Y parameters, because with such an interconnection, the y parameters of the series interconnected two ports consist of nothing more than the y parameters of the individual two ports added together in just the same way we did for the individual z parameters when we had a series interconnection. And here's a circuit example, a common circuit that can be treated as a shunt connection of a pair of two ports. A transistor, there it is, there's our transistor with a feedback resistor, a resistor that connects the collector of the transistor to the base. I drew that resistor down here so that you could consider it to be 2-port B in the upper diagram up here. But remember, it's the same as connecting that resistor up here, and that's a very common circuit configuration. So, in order to figure out the y parameters of this transistor with a emitter feedback, find the y parameters of the transistor and find the y parameters of the resistor and add them up element by element, and there you have the y parameters of the overall circuit. Okay, hybrid parameters, the H parameters. When you are dealing with a pair of two ports in a hybrid interconnection, then the hybrid parameters are the ones to use. Then the hybrid parameters of the total overall interconnected pair of two ports are nothing more than the sum of the hybrid parameters of the individual two ports. And what do we mean by hybrid interconnection? Well, it's like a series interconnection at port 1, and it's like a shunt interconnection at port 2. That's the hybrid interconnection. And as I just mentioned, the overall hybrid parameters for the hybrid interconnected pair are found as the sum of the individual hybrid parameters of the individual two-port networks. And we do find circuit examples of hybrid interconnected two ports. You can consider two transistors connected in this fashion, transistor 1 and transistor 2, or transistor A and transistor B, connected as shown here. This is a Darlington pair of transistors. This is a very common type of a circuit to encounter in electronics. And it is a hybrid interconnection. You see the series interconnection on port 1, and you see the shunt interconnection on port 2. So if you know the hybrid parameters of transistor A and the hybrid parameters of transistor B, the hybrid parameters of the overall Darlington pair, nothing more than the sum of the hybrid parameters of the two transistors. Now, of course, a given circuit can contain one pair of two ports that are series interconnected, and then another two-port connected to that in a shunt type interconnection, and then another two-port interconnected to that whole circuit in a hybrid interconnection, and so on and so forth. In that case, it's most convenient to use the z parameters when figuring out the overall parameters of the series connected pair. So I'd do that one in terms of z parameters. But now that's followed by a shunt interconnected two-port, where y parameters are the most convenient to use. So what I would do as an intermediate step is, once I found the z parameters of the series interconnected pair, I do the conversion listed in the textbook using the table there, from z parameters to y parameters, to get the y parameters of that first pair, and then combine that first pair with the next two-port that's in a shunt interconnection using y parameters, which are most convenient for shunt interconnections, to find the y parameters of the overall 3 two-ports interconnected. Now let's say there's a fourth two-port connected in hybrid interconnection. Well, convert those y parameters I just found, now convert them to h parameters, and use the h parameters next to calculate the overall h parameters, including the fourth element that was hybrid interconnected, and so on and so forth, doing parameter conversions at each step. Okay, now here's the fourth and final type of interconnection I'm going to talk about, the cascade interconnection. This is the one that you may have thought of when you first heard the word series interconnection. We call that a cascade interconnection. It's a very common interconnection. You see two ports connected like this an awful lot in networks. There's two-port A. It's port 1 terminals and port 2 terminals connected directly up to two-port B. Its input terminals, or port 1 terminals I should say, and port 2 terminals for two-port B. We use the usual passive sign convention to define current directions for voltages, well, current voltage polarities and current directions for voltages and currents at the ports of two-port A and two-port B. So there's voltage and current port 1 for two-port A, voltage and current port 2 at two-port A, similarly for two-port B. Notice that the voltage at port 2 for two-port A is the same as the voltage of two-port B at port 1. That's supposed to be just one single straight piece of wire connecting the port 2 of two-port A to port 1 of two-port B. So V2A is equal to V1B. However, in terms of currents, check this out. I2A is equal in magnitude to I1B, but defined in the opposite direction. You always define currents flowing into the terminal with the positive polarity in any given two-port. So I2 of two-port A flows into port 2 of two-port A. I1 of two-port B is defined as flowing into port 1 of two-port B, and they are negatives of one another, since that's one and the same current, just defined in two different ways, defined to be in different directions. All right, this might go a little ways toward explaining why the current I2 in the overall definition of the ABCD parameters, why that current I2 appeared with a minus sign in defining the ABCD parameters. Because the biggest reason for using the ABCD parameters, the chain parameters, is in situations where you have cascaded interconnected two ports. And you want to be able to do calculations with cascaded interconnected two ports and find overall ABCD parameters for the cascade interconnected pair. And it's easiest if you can absorb that minus sign into the definition of the ABCD parameters, so that when you find, let's say, I1 and V1, you're actually finding it in terms of the current flowing into the next two-port and the voltage across the terminals of the next two-port, the negative of the current that we normally define at port 2 of the first two-port. So that's the basic reason underlying the presence of that negative sign in the definition of ABCD parameters. Here's a simple circuit example. A resistor shunt connected to the collector of a transistor. So here's two-port A, here's two-port B, the resistor. Cascade interconnected. The voltage at port 2 of the transistor is the same as the voltage at port 1 of the resistor. And the current flowing into port 2 of the transistor is the same, well, actually the negative of the current flowing into port 1 of the resistor. So we've got a cascade interconnection here. And the overall circuit within the dotted box here has ABCD parameters, chain parameters, that are given by not the sum now, but actually the matrix product of the chain parameters of the transistor and the resistor, or in general, the matrix product of the ABCD parameters of two-port A times the ABCD parameters of two-port B. Note this is a matrix product, so that A of the overall cascade interconnection is equal to A of two-port A times A of two-port B plus B. Well, it's the matrix product. You know how to do the matrix product of a pair of 2x2 matrices. Make sure you do know how to do that matrix product. Okay. We're going to find it useful to have a table of ABCD parameters to refer to in some of our calculations. Here are some very common circuits and their corresponding ABCD parameters listed one by one in this table. The first circuit is nothing more than a single series resistor. So think of drawing a dotted box around this portion of that circuit. You can define voltages and currents at the two ports as usual and calculate A, B, C, and D as usual. And here's what you'll find. A is equal to 1, B is the impedance value Z, C is 0, and D is equal to 1. If you have a shunt admittance as the circuit in question, then here are the ABCD parameters of that shunt admittance. Here is a P-type interconnection of three impedances, ZA, ZB, and ZC. And the question here is, what are the overall ABCD parameters of the entire circuit? Here they are in terms of the impedances ZA, ZB, and ZC. Here is another way of connecting together three impedances. Now this is the pi type interconnection. This is the type of interconnection that we looked at in the example that I just wrote down. The table is in error at this point. Get your pen out right now and make a change for me if you would. They called this element YB and this element YC. They got the two of them mixed up. YC belongs here. This should be YC at this location. Similarly, that's the one that we should call YB. This should be YB at that location. So, in your class notes, cross out the B here and write a C. And cross out the C here and write a B. Then the formulas that we have here for the ABCD parameters are correct. Otherwise, they are incorrect. This was a simple notation error on the part of the textbook that I got this figure out of. Note that, A, B, and C are in the configuration shown here. A and B are on the arms of the T, and C is in the middle. Should be the same thing here. A and B are on the arms of the pi, and C should be in the middle. Okay, not the way they have it labeled here, but the opposite labeling with B and C. By the way, this is the D parameter. There it is. And what I found was D was equal to Z1 plus Z3 all divided by Z1. Is that what I got here? Do you get the same thing here? ZA plus ZC divided by, let me see, what did I call them? ZA divided by, ZA plus ZC divided by ZA. Can you get that from this formula in terms of y's? Check it out. Make sure that this gives you the same result as the one I just got done deriving in class. Here is another useful circuit element for us to have the chain parameters of. Inside of the two-port network is nothing more than a transmission line of length D. So of length L, excuse me. So we've got a transmission line with characteristic impedance Z0, phase constant beta. These are always specified when you choose a transmission line. These are known quantities. And here's the length of the transmission line, another known quantity. And we would like the ABCD parameters for this finite section of transmission line. Here they are. Here are the ABCD parameters for that length of transmission line. One final circuit that's given in this table is the N-to-1 transformer. Here are the ABCD parameters for an N-to-1 transformer. We won't use this transformer in any of our circuits in this class. Oops, what did I do? Wow, 2 pages. There we go. All right. Now, enough said about the low-frequency parameter sets. We're going to talk about a parameter set that's of more use at high frequencies. The low-frequency parameter sets aren't appropriate at RF frequencies because they become very difficult to measure and may actually end up damaging the circuit that you're trying to measure if you measure them in their normal fashion. Because all of these low-frequency parameter sets are defined in terms of open circuit and short circuit measurements. And at RF, as we'll find later, true open and short circuits are actually kind of difficult to obtain in the laboratory. Very tricky to get a good open circuit or a good short circuit at RF. We'll talk more about that in just a little while. Not only that, but if you do happen to get a good open circuit or a good short circuit for an awful lot of devices of interest, especially things like transistors and other types of active devices, either a short circuit or an open circuit can cause them to either oscillate or possibly to oscillate with growing oscillations, exponentially growing oscillations, oscillations that grow unboundedly, causing the device to burn out. And so even measuring the low frequency parameters of a lot of RF devices of interest can damage or destroy the devices that you're trying to measure. Instead of these low frequency parameter sets that depend on open and short circuit measurements, we're going to use the scattering parameters, which don't depend on open circuit and short circuit measurements. But before we introduce the scattering parameters, let's talk about transmission lines for a few minutes, because transmission lines go hand in hand with circuits and measurements at RF frequencies. We talked earlier about radiation at RF. It's one of the most troublesome problems in RF circuit design because it causes loss and interference or crosstalk in circuits. And so we use transmission lines rather than just regular pieces of wire to connect different points, different locations in RF circuits. Transmission lines are used to guide electrical signals from one point to another in an RF circuit or in any type of a RF geometry from one point to another with the minimum of radiation and subsequent loss and crosstalk and so on. The most common type of transmission line in use is the twin wire pair, 2-wire pair transmission line. Just a pair of wires is shown here, conductors of radius A and separation capital D, connected from one point in the circuit to another, guiding voltage waves and current waves and electromagnetic fields from one point to another in this direction, the direction of the transmission line. The transmission line sets up electric fields that surround it and magnetic fields that surround it. The fields have the appearance shown here. And for a twin wire pair like this, these fields are called TEM fields. TEM. You've probably heard this terminology before. It stands for transverse electromagnetic. What this means is that the electric field lines and magnetic field lines all lie in the plane of the page here, where the wires point vertically, directly into and out of the page. The fields are transverse, perpendicular to the direction of propagation, the direction of transmission for the transmission line. And it turns out that in problems where the fields are TEM fields, you can come up with nice closed-form solutions to Maxwell's equations in these cases. There are nice closed-form solutions for the electric fields and magnetic fields for the twin wire pair, and corresponding exact formulas that can be used to calculate those fields at any point in space. And if you can calculate the fields, you can also calculate the voltages and currents. And there are exact closed-form expressions for voltage and current at any point for the twin wire line. These twin wire lines are in more common use than you would think by looking at this simple setup that I have here. Because, if we could turn to the overhead for just a moment, they are often, these days, used in so-called twisted pairs of twin wire transmission lines. The simplest example I could give is somewhat difficult to draw. Something like that. What that's supposed to be is a pair of wires that's just twisted up on itself. Why twist the pair of wires? Well, the basic idea is that if you look at those field plots for the twin wire pair, the fields extend pretty far away from the pair of wires. If you can get those wires to be as close as possible to one another, the majority of the fields will be concentrated in the area between the two wires. And twisting those wires together is going to get them about as close together as you can possibly get them. Twist them up tight, and they're going to be pretty close center to center. Okay. You define your positive and negative terminals at the ends. Now, this is a basic two-wire twisted pair. Practical twisted pair transmission lines these days, however, consist of first of all, a pair of these twisted wires. Did I already blow it? Let me see if I can draw this thing. It takes a lot of practice to be able to draw a twisted pair of wires. There's one of them. And there's another one. I'm just going to try to redraw the same thing next to it. So we got a pair of twisted wires as shown here. You're not going to be able to see this. Now, why use two of them? Here's the idea here, is that we generally, when we're interconnecting a computer and the internet or a modem or router or something of that nature, we usually are transmitting and receiving signals. And you can do both at the same time. And you would like to have the minimum amount of interference between the transmitted signals and the received signals. So make a twisted pair devoted entirely to transmitting signals in one direction, and a twisted wire pair devoted entirely to receiving signals, signals that are transmitted from the other direction. Okay, you got 4 wires now. Actually, the way that twisted pairs are used today has a total of 8 wires in there. They've got four more wires, and those 4 more wires, I'm not going to draw them all. I'll draw one pair because I'm getting tired of drawing these pairs. These are twisted along with each pair. So think of having actually 4 wires in there, in that bunch. And those 4 wires make up the transmit side, and similarly 4 wires like that make up the receive side. Now, the idea here is that these dummy wires, these grounded wires, are really close to the transmit wires or the receive wires, which are the live wires. And any fields that aren't confined between the 2 live wires for transmit and receive, any fields that aren't confined right between those 2 wires will likely end up terminating on those ground wires rather than being radiated away from the 4-wire bunch now. So, they take 4 wires, twist them together to form one big twisted mess of 4 wires. Take another 4 wires, twist them together. Ground 2 at each end from each group of 4, and use the other 2 from each group as the live wires for your transmit and receive channel. And now take that 2 groups of 4 wires and put them inside of some sort of a sheath. Hook up what looks like a phone jack onto each end. It's a little bigger than a standard phone jack, but it looks just like a phone jack otherwise. And what you've got is the basis of 10 base T or 100 base T Ethernet connection cable. RJ45 connections. You've probably heard of these. Most of you have probably made use of those type of transmission lines. They're cheap and they're pretty good. They're fairly low loss and have fairly small radiated fields. They're based on simple idea of twin wire transmission line, just fancied up a bit. Twisted together with some ground wires to help isolate stray fields, and split up into transmit and receive channels to further isolate and prevent crosstalk in signals transmitted and received. So there's the twin wire pair. This is the transmission line that most people think of when they hear the words transmission line. It's the coaxial transmission line. Conductor of radius A as the center conductor, outer conductor of inner radius B and outer radius C, some sort of a dielectric in between the inner and outer conductor of permittivity epsilon r, dielectric constant epsilon r, where the actual permittivity is epsilon 0 times epsilon r. Here's what the field lines look like. It's again a TEM transmission line, transverse electromagnetic. Those fields are just in the XY plane if the Z direction was perpendicular to the plane of the page here. They really do lie in the plane of the page. And you can solve for those fields exactly. You'll find the solution for this one as a standard example in any undergraduate fields and waves textbook. You can find the fields in closed form exactly. You can find corresponding exact closed form solutions for voltage and current, and so on for the coaxial line. A very handy type of transmission line, commonly used in situations where loss is paramount, because field confinement here is excellent. For the case of an ideal perfect conductor, there would be absolutely 0 fields outside of that outer conductor. All of the fields would be entirely confined to the dielectric in between the inner and outer conductors. So no chance of crosstalk whatsoever when you're using coax, as long as the metal is a good conductor at RF frequencies. Losses are very small because there's not much of a radiated field, and we usually assume that the dielectric that's placed inside of the coaxial line is a pretty good dielectric with very small losses, which is another thing that's very easy to realize in practice. Coaxial lines are useful because of the field confinement, also because of their power handling capability. You can pump quite a few watts of power down a piece of coax. A type of transmission line that has been of more and more interest lately is the microstrip transmission line. And the basic microstrip transmission line geometry is as follows. You take a ground plane. This is a planar sheet of conductor, assumed to be infinite in extent when doing analysis with microstrip. You put on top of that conductor, you lay a layer of dielectric of permittivity epsilon r, dielectric constants epsilon r, height d for the dielectric layer, and then on top of that place a conducting strip, a strip of conductor of width w and thickness t. Then this configuration acts as a transmission line. You can place a signal source at one end of the microstrip line here. The signal will propagate down the microstrip transmission line, and you could place a load or some other portion of the circuit at the other end of the microstrip line. Waves are guided along the direction of the upper conducting strip of the microstrip line. Here's the field configuration. Now, this is not a TEM transmission line. So the field lines that I have shown here are just the fields that are in the XY plane. But there are fields that exist in the direction pointing directly into the page or directly out of the page as well. So this is a non-TEM transmission line. Note that the fields are mainly confined to the area between the microstrip transmission line and the bottom conductor, which is often called the microstrip ground plane. So the fields are concentrated between the conducting strip and the ground plane, but they do exist in the region up above. You can make the concentration of fields greater in the microstrip line by increasing the permittivity, increasing the dielectric constant of the substrate. For example, here's a Teflon type of substrate where epsilon r is 2.55. This is alumina substrate with permittivity of 10, and you can see the fields are much stronger between the strip and the ground plane for the higher value of permittivity. The fact that the fields are not TEM fields means that analysis of the microstrip line is quite a bit more complicated than analysis of the twin wire line or the coaxial transmission line. Very much more involved. Why deal with that complicated problem at all? Well, that's because the microstrip line is basically, it's ideally suited for an awful lot of RF circuits that are in use today and that we're going to be looking at in this class. RF circuits that are integrated RF circuits. RF ICs. Because this is the type of situation you get with integrated circuits. You have a substrate with possibly some oxides built up on top of it, and you place metallizations above and below in typical integrated circuits, and so you could imagine having one integrated circuit element, transistor, or some other type of device hooked up here, and another integrated circuit element hooked up here, and integrating this microstrip transmission line using the same fabrication technology you use for the integrated circuit. So the microstrip line is ideally suited for microwave integrated circuits. Okay, more complicated mathematically, but nonetheless very useful and very practical. We'll take a look at formulas for voltage and current and impedance and so on for the microstrip line. They're pretty messy looking formulas, but we'll take a look at them real soon now. Okay, we're about out of time. Before we end, let me make note of the fact that there is problem assignment number 1 ready and waiting for you on Blackboard. Homework set number 1 in the file homework on our Blackboard website for 5371. Look it up and print out that homework set. It is due a week from today. That's Thursday the 24th I'm talking, not Wednesday. Thursday the 24th is the due date. Make sure that you have your solutions ready and with you when you come to class a week from Thursday, because at that time I'll have my solutions ready, and by the time class is over, I'll have those solutions posted on the Blackboard site for the course, and probably have a new homework set for you by next Thursday as well. Okay, so that does it for today, and we will pick it up from here on Tuesday.